Welcome to Course 101, TiDB Technical Essentials. This is Module 4, Placement Driver. My name is Jeff, and I am your instructor for this module. After completing this module, you will be able to describe PD architecture and functions, describe TSO allocation, describe scheduling processes, describe the relationship between labels and high availability. The placement driver is the central controller of the TiDB database and is the brain of the entire TiDB cluster. The placement driver is most commonly called the PD. In the TiDB database cluster, the PD is responsible for storing metadata, assigning global IDs, transaction IDs, global timestamp or TSO generation, service discovery, collection of information such as overall topology of the cluster, real-time data distribution, and hotspot status, and scheduling data in TiKV nodes. In addition, the PD is the home of the small web server that runs TiDB dashboard. Next, let's take a look at the architecture of the PD. PD itself consists of at least 3 nodes. It is okay to have more, but you cannot have fewer than 3. It is recommended that you deploy an odd number of PD nodes. PD supports auto failover by integrating the etcd database, that's etcd database. So there's no need to worry about a single point of failure. At the same time, PD uses etcd's raft algorithm to ensure strong consistency of data. This means there's no reason to worry about data loss. Finally, in a PD cluster, a node with a leader role provides stateless services to the outside world. All operations are triggered passively. Even if the PD leader goes down, with the help of PD's election mechanism, the newly elected PD leader can immediately serve the outside world without considering any intermediate state. Before we move on, we need to define some words. This should be familiar because we covered some of these terms in the TiKV module. The first is store. In PD, store refers to a storage node in the cluster, that is, a TiKV node. Note that the store and TiKV instances are strictly one-to-one. Even if multiple TiKV instances are deployed on the same host or even the same disk, these instances will correspond to different stores. Next, region, peer, and raft group. Each region is responsible for maintaining a continuous segment of a cluster's data, by default no more than 96 megabytes. Each replica stores multiple copies of the data in different stores. The default configuration is 3 replicas, each of which is called a peer. So that means that every bit of data is replicated 3 times to help keep it safe. Multiple peers in the same region synchronize data via the raft protocol. So peers are also used to refer to members of a raft instance. TiKV uses multi-raft mode to manage data. That is, each region corresponds to a raft instance that runs independently. We also call such a raft instance a raft group. Next up, leader, follower, and learner. These are raft terms, so we've covered leader and follower. So they correspond to each of the 3 roles available to a peer. The leader is responsible for responding to the client's reads and writes request. The follower passively synchronizes data from the leader and elects a new leader when the leader fails. We haven't discussed the learner role. Learner is a special role that only participates in synchronizing raft logs and does not participate in voting, and only exists briefly in the current implementation to add an intermediate step to the replica. Next, we will discuss the main functions of the placement driver. They are: PD provides metadata storage for the entire cluster TiKV. Information such as the region corresponding to the key range in the TiKV store, where the region, including information such as leader, is located, are stored in PD. For example, TiDB server obtains route information from PD and then accesses data on the specific TiKV node. In addition, PD stores the topology information and label information about the TiKV nodes. We will discuss this later. Next, PD assigns a global ID and a transaction ID. So PD assigns the global IDs we use, such as store ID, region ID, peer ID, table ID, index ID, etc., and the transaction ID of the distributed transactions. Next, PD generates a global timestamp, or TSO. TSO is a global timestamp that guarantees the order of transactions in the database. This is one of the most important responsibilities the PD has. We will cover the details later. Next, PD collects cluster information before scheduling. The TiKV node periodically reports the status of the cluster to PD. The PD is responsible for scheduling the region between TiKV nodes according to the relevant status. We will introduce details later. Finally, TiDB dashboard service is provided by the PD. We mentioned this on a previous slide. The PD hosts a small web server that runs the TiDB dashboard. Recall that the TiDB dashboard provides information regarding the TiDB database. In summary, PD is the equivalent to the general control center of the TiDB database. In later sections, we will focus on the functions of generating global timestamps, or TSOs, and scheduling. Since PD stores all TiKV cluster information, it naturally provides routing functions to the TiDB servers. Routing means that data is written to and read from the TiKV node where the data should live. So how does TiDB server write a value to the key? The first step is the TiKV client, in this case TiDB server, queries the PD so that it knows which region owns the key value. PD returns the metadata information for the region. Next, the TiKV client has a region cache that caches metadata, so there's no need to get it from the PD every time. It will only do this once the cache is empty. This makes it faster. Next, let's look at TSO assignment, TSO concepts. So TSO is a global timestamp. The TSO is the cornerstone of TiDB's distributed transaction implementation. Therefore, for PD, we first need to ensure that it can quickly and massively allocate TSOs to the transactions. At the same time, we need to ensure that the allocated TSO must be monotonically increasing. Monotonically increasing means that the TSO is always increasing or remaining constant and never decreasing. TSO is a 64-bit integer, or int64, that consists of physical time plus logical time. Physical time is the current Unix time in milliseconds, while logical time is a counter with a maximum of 1 to 18. In other words, for 1 millisecond, PD can be allocated up to 262,144 TSOs, which satisfies the vast majority of cases. All TiDB server and PD interaction is carried out through a PD client thread module. The PD client thread module is responsible for obtaining a TSO from the PD in batch. The general workflow process is as follows. Let's take a look at the arrow marked 1. When the TSO requester transaction needs to request a TSO, it first sends the request to the PD module client, or client module. Arrow 2 shows the PD client module immediately returns the TSO to the requester using a TS_future object. Arrow 3, after receiving the TS_future, the TSO requester caches it and immediately starts to parse and compile the SQL statement. Arrow 4, once the parse and compile process completes, TiDB server calls the wait method of TS_future to wait for the TSO to return. Arrow 5, while the TSO requester waits, the PD returns the TSO to the PD client asynchronously through a remote procedure call, or Google Remote's procedure call. It is important to understand that this is not a single TSO request. The PD client will request TSO from PD immediately. When multiple requests arrive at the PD client at the same time period, and it's very short, the PD client will proceed to batch processing. These requests are sent only once as a batch request. But if the PD client fails to receive TSO requests for a long time, requests are still sent to PD one by one. This corresponds to arrows 3 and 5. Finally, we get to arrow 6, get TSO. Once the PD client receives the TSO from the PD client tries to return the TSO to the corresponding TSO requester. If the TSO requester happens to call the wait method of TS future, then the TSO requester gets the TSO. In summary, the allocation of the entire TSO is an asynchronous process. You can tell that this process is important. In fact, it is so important that we need to ensure that there is not a single point of failure in the process. As we said, PD clusters can ensure that a new leader is selected immediately after the current leader node goes down. Selecting the new leader is handled as part of the RAFT algorithm. You're probably asking yourself, how does this new leader avoid distributing a TSO that breaks the monotonically increasing rule? That is, distribute a TSO that goes back in time. The current TSO of the old leader must be stored somewhere. The storage must be highly reliable, so TiDB uses the etcd database. This brings up another question. Is it necessary to save a timestamp for every TSO generated by the PD? The answer is thankfully no. The speed at which timestamps are generated is directly related to disk I/O performance, and there are bottlenecks. So how do you solve the performance issues? TiDB uses a pre-allocation time window to handle this. Let's discuss the process. Assume the current PD, the leader, has a TSO of 700. We're using 700 to make the example easier. An actual TSO looks much different. And the PD has stored the value in etcd for an allocatable time window. The span of the time window can be specified using a parameter. The default configuration of the system is 3 seconds, and the example uses the default configuration. So the starting point of the window is 700, and the end point of the time window is at 703. After writing to etcd, the PD will get an allocatable time window from 700 to 703. This is 700 plus the default of 3 seconds. In this time window, PD can use the physical time of the system as a high level, splice the logical time accumulated in memory, and assign a timestamp to the outside. This design means that all PDs are assigned a high timestamp physical time, that is, always less than the maximum value stored in etcd. If the PD leader goes down, the new master can read the maximum value stored in etcd and apply for a new allocatable time window based on this value. So the timestamp assigned by the new master will be larger than the old master. In addition, in order to reduce the communication overhead, each client can request multiple timestamps at a time. The number of timestamps is passed by the client to the PD as a parameter. It's important to note, however, that once cached on the client, the clock between multiple clients is no longer strictly monotonically increasing. As a distributed, highly available database storage platform, we must meet the following requirements. Fixed number of replicas. Replicas need to be distributed among multiple nodes. After adding a new node, you can migrate a replica from an existing node to another node. After the node goes offline, the data on the node needs to be migrated. In addition, we must meet the following performance requirements. Maintain a uniform distribution of leaders throughout the cluster. Maintain uniform storage capacity of each node. Maintain uniform distribution of hotspots. Control the speed of balance to avoid affecting online services. And finally, management node status, including manual online-offline nodes and automatic downlink of failed nodes. In order to meet these requirements, we first need to collect sufficient information, such as the status of each node, information about each RAFT group, statistics regarding services across operations, and others. Secondly, we need to set up some policies. Based on this information and scheduling strategy, PD will formulate a scheduling plan that meets the requirements described above as much as possible. And finally, some basic operations are needed to complete the scheduling plan. Since TiKV is not responsible for allocating regions, let's repeat that. TiKV is not responsible for allocating regions. The PD is responsible for this. only PD has a global perspective, so only PD nodes can complete this task. So the whole process is as follows: information collection, generate a schedule, and execute the schedule. Let's take a look at each of these steps. Okay, so first up we're going to talk about information gathering. TiKV nodes periodically report two types of heartbeat messages to the PD. The first is the store heartbeat. The second is the region heartbeat. The store heartbeat contains the basic information of storage, capacity, remaining space, writes, reads, traffic, etc. The region heartbeat contains data such as region range, replica distribution, replica status, data volume, and reads and write traffic. PD combines this information and stores it for the scheduler to make decisions. Once we gather this information, it can be passed along to the PD so that it can generate a schedule. Once we've gathered information, we can generate a schedule. Different schedulers start from their own logic and requirements. They consider various restrictions and constraints to generate operators that execute the schedule. So what is an operator? Well, an operator is a collection of operations that serve a particular scheduling purpose that are applied to a region. Operators can be computationally generated by PD or created manually by an external API. Here are some situations that will result in an operator being created. 1. Balance. This means that we evenly distribute regions across all stores in a cluster. It can be divided into two types. The leader focuses on the leader of a region, which can be thought of as the purpose of dispersing pressure of processing client requests. This is volume of client request. Number 2, the region focuses on each peer in the region with the aim of spreading the pressure on storage and avoiding disk fullness. Next up, hot region. For write hotspots, hotspot scheduling attempts to disperse the peer and leader of the hotspot region at the same time. For read hotspots, since only the leader carries the read pressure, the hotspot scheduling attempts to disperse the leader of the hotspot region. Next, cluster topology. The topology that makes PD aware of the distribution of different nodes is to distribute individual replicas in different regions as much as possible through scheduling to ensure high availability and disaster recovery. For example, if a cluster has 3 data centers, the safest way to schedule is to place the 3 peers of the region in different data centers so that if any data center fails, it can continue to provide services. Next, scale in. Scale in is when a store is ready to be taken offline, that is, the size of the cluster reduced, and the store is marked as offline with the command. At this time, PD migrates the region on the node to be offline to another node via a schedule. Next up, failure recovery. Failback means that when an existing store fails and cannot be recovered, the distribution of peers to regions on the corresponding store will cause a state of missing replicas. At this time, PD needs to create replicas for these regions on other nodes. And then finally, region merge. Region merge refers to the process of merging adjacent small regions by scheduling to avoid large amounts of small regions or empty regions consuming system resources after deleting data. In the diagram a few slides back, I called this executing a schedule. Performing a schedule is another way to say this. The operator spawned in PD does not immediately start issuing and executing commands. Instead, it first enters a wait queue. According to the configuration, the operator is removed from the waiting queue at a certain concurrency and executed. The process of execution is to send, in turn, each step of the operator to the leader of the corresponding region. When the operator finishes executing, it is marked as finished or the timeout is marked as timed out and removed from the execution list. A label is a way of telling TiDB database how to configure itself. Think of it as whispering special instructions into its ear. In order to illustrate what labels do, let's take a look at our diagram. We have 3 data centers, DC1, DC2, and DC3. This represents 3 independent data centers. Racks 1 through 6 represent 6 racks. TiKV 1 to TiKV 12 represents 12 hosts. Each host has 1 TiKV instance. Next, let's look at the topology, how the regions are distributed across data center and racks of 3 regions. By default, each region has 3 replicas. Region 1 has 1 leader and 1 follower on the second host. TiKV 7 and TiKV 8 in rack 4, and the other follower is in rack 6 in data center 3. Take a look. Feel free to pause the video. Do you see the problem? The risk of this deployment is if there is a problem with data center 2 or if there is a problem with rack 4, it will cause region 1 to become unavailable. All right, let's take a look at another example. Region 2 has 1 leader that is in data center 2 and 2 followers that are in data center 1. These 2 replicas are in different racks. This means if there is a problem with either rack, the data in region 2 can be accessed. This is a stronger arrangement than region 1. However, if something happens to data center 1, then region 2 is no longer available. Region 3 has 1 leader and 2 followers. All are in different data centers. This means that if there's a problem with the data center, rack or host, it will not affect the availability of region 3. You can say region 3 is the most robust. Comparing the distribution of region 1, region 2, and region 3, we found that different region distributions have an impact on availability, especially if the metadata of the database, for example, the information schema, is stored in a region that goes down. It could make the database unusable. We know that the original distribution of regions is randomly deployed by PD. PD nodes only guarantee that multiple replicas of a region will not be placed in the same TiKV node. It does not know about data centers and racks. Fortunately, we can guide the PD to place data in specific data centers and racks by using labels. We can set a label for each TiKV instance to identify which host and which rack of which DC it is located. The PD node specifies the format of the label so that when the PD node initially distributes the region, it can perceive the location of the data center, rack, and host according to the label set on the TiKV node. This helps implement high availability for our TiDB database cluster. Now that we understand what labels do, let's take a look at how to set them. First, in the PD node, we need to identify the format information of the label. That is, the source information as follows. So here's an example. We have replication, we have location labels, and then our parameters include DC, a zone, rack, and a host. Among them, DC, rack, and host respectively indicate a data center or a rack and host. These are all physical locations or devices which are very understandable. However, zone is actually a logical concept used to denote the smallest location where a replica can be isolated, and the number of them is always the same as that of the replica. For example, if we have a default of 3 replicas and we have 3 data centers, then we will set up 3 zones, each zone corresponding to a data center. The replicas will be placed in the different zones. If we have 1 data center but we have 3 racks, then we can also set up 3 zones, 1 rack for each zone, and the replicas are placed in the different racks. Second, let's take a look at the TiKV configuration YAML file. Here's how we will interpret the contents of this file. We have a host up front, rack 1, cabinet in data center 1, where the IP address is 10.63.10.30. This is host number 1, zone number 1. When the PD sees the locations of these 3 hosts, it's possible to place 3 replicas of the region on 3 hosts for maximum high availability. Now you know how to make our data storage more resilient. We have covered a lot of material during this module. I feel confident that we've met all of the objectives defined at the beginning. We can describe the PD architecture and its functions. We can describe TSO allocation, we can describe the scheduling process, and we can describe the relationship between labels and high availability. Thank you for taking the time to view this module. We hope you enjoyed it and learned a lot.